Hi, everyone. Welcome back. My name is Professor Andrew Timming, and I want to extend a warm welcome to you for joining me to learn a bit more about regression analysis in a bivariate context. This is a lecture that corresponds to Chapter 8 of my textbook, Applied Statistics. You should already have listened to Lecture 1, the previous lecture, which gave you a good foundation for understanding regression analysis. We looked at two interrelated methods, simple regression and Pearsons R. And in this lecture, we will extend the knowledge that you learned from lecture 1 in chapter 8. We will calculate and interpret B in the case of simple regression and Pearsons R. So let us begin, shall we? Here you can see the textbook that we are using, Applied Statistics, Business and Management Research. And as I said, the lecture that you're currently listening to corresponds to Chapter 8. If you've not already read Chapter 8, I would urge you to do that before proceeding. But let's not waste any more time and jump right into the material. All right. So let's start with a research question. This research question should be familiar to you if you have read Chapter 8 of the textbook, because the question is asked and answered using both simple regression and Pearson's R in Chapter 8. The question is employee attractiveness positively correlated with income? So take a few moments to think for a moment what you might expect based on these two variables. Are you going to expect a positive relationship? Are you going to expect a neutral relationship, as is to say no relationship at all? Or are you going to expect a negative relationship? All right. So just keep this in the back of your mind as we proceed in answering this question. As you can see, embedded into the research question, we have, as you would expect, two variables. Our independent variable is employee attractiveness, and this could be measured in any number of ways. For example, you could ask a line manager, how attractive would you rate this employee on a scale of 1 to 7, where 1 is not at all attractive and 7 is extremely attractive. And our dependent variable is a simple scale level measurement of the employee's income. So you could simply ask, how much does this employee earn annually? All right, let's start with an example of simple regression to answer this question. And then once we've done that, we'll move on to Pearson's R. You can see at the top left-hand corner of this slide the basic equation for simple regression. It may be an equation that you're somewhat familiar with. You may have come across this equation at some point during your studies. And the equation is y equals bx plus a plus e. So let's break down the different components of this equation. You already know what X and Y mean. So in the context of our research question that we're looking at, X refers to perceived attractiveness and Y refers to income, right? But what about the rest of the equation? So B is what we refer to as the slope or the coefficient. And B is a number that signals to you whether the relationship between X and Y is positive, neutral, or negative. So if B is a positive number, that suggests a positive relationship between X and Y. If B is a negative number, that suggests a negative relationship between X and Y. And if B is 0, that suggests a neutral relationship between X and Y. The y-intercept, so that's A in the equation, is the point at which the line of best fit touches the y-axis. So think back to the scatter plot that we learned about in our previous lecture. In our scatter plot, we drew a line of best fit, which is the line that minimizes the residuals between the data points and that line. If you were to extend that line all the way to the y-axis, that would be your y-intercept. Finally, E in this equation is an error term. That's essentially recognizing that we're not going to be able to perfectly explain y on the basis of x, and that there's any number of other variables that can also explain y that we haven't measured and therefore are not included in our analysis. But for now, we can set aside E because it's just there to remind you that you're not explaining the whole picture, right? It actually plays no role in our calculation. So from here on out, let's set E aside. Okay, so the first thing we need to do to solve for Y is to solve for B, right? So we need to calculate B, which is our coefficient, our slope. And you can see the equation there, b equals n times the sum of x times y minus the sum of x times the sum of y divided by n times the sum of x squared minus the sum of x and then squared. So you can see the different components of this equation on the left. Again, it seems a bit intimidating when you first look at it, but if you take it step by step, it's actually not that difficult. So on the right, we have our data. We have 20 respondents in our sample, so n equals 20. We have our x values. Remember, those are all values between 1 and 7, where the higher number equals more attractiveness. And then the y value in the next column over, that's the income associated with each respondent. And then to help facilitate the calculation of this equation, I've squared each of the x's. So x squared is the next column over. And then the last column is x times y. So I've taken x and multiplied it by y. And then at the bottom, you'll see some key data as well. The sum of x, the sum of y, the sum of x squared, and the sum of x times y. So now that we have done these simple calculations that you can see on the right-hand side in the data set, it's simply a matter of plugging in those values into the equation on the left-hand side of this slide. So I'm not going to go through every single step in this equation because it is quite involved. But if you follow along from the top all the way to the bottom, you'll see how I solved for B given these values of x and y. So you're simply plugging in the various information that you can get from the data set on the right into the equation on the left. And if you plug that information in and you work your way down, you find out that B, our slope or our coefficient, is 7,857.37. So what does that mean? What does that actually indicate when we find a slope or a coefficient like that? What it means is that for every 1 unit increase in x, y increases by the amount demonstrated, the amount shown in B. So it's a little bit complicated, but let me try and explain here. So our B is 7,857.37. So that actually is in the form of dollars, right? So what we're saying here with this particular B coefficient is that for every 1 unit increase in x, which is our attractiveness, that is to say from 1 to 2, from 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 7, we see a y increase, a salary increase of $7,857.37. So this holds at all intervals within x. Now, the important point to note here is that this is a positive number, and therefore we can assume that there is a positive relationship between x and y. As attractiveness goes up, income also goes up. But again, the point is not whether or not we find a positive relationship in our sample. The point is whether or not the positive relationship in our sample generalizes to the population, and we can only tell that by looking at the p-value that's associated with our coefficient here. And if the p-value is less than 0.05, then we will assume that this result is statistically significant. Now, having calculated b, we still can't use the regression equation, the simple regression equation, to predict y. And the reason is that we still need to calculate a. We need to identify or calculate the y-intercept, or the point at which the line of best fit crosses or touches the y-axis. Now, there are multiple ways you can do this, but the easiest way is just to use some simple algebra to rearrange the equation on the top, y equals bx plus a, into another equation that we can use to solve for a, which is a equals y, the average of y bar as we would call it, minus b times the average of x. So we can find this information here. So I've taken the liberty of calculating the average of y, that's 46,750. The average of x is 4.27, and of course we already know b. So taking the equation from the previous slide and solving for a, you can simply plug in those numbers, and if you do the math, it's very simple math, a little bit of multiplication and subtraction, you discover that a equals 13,199.03. So what this means, again, is that when we fit the line of best fit for these data, the line of best fit is not only going to tell us the slope, that is to say, for every 1 unit increase in x, what's the corresponding effect on y, but it's also going to tell us the point at which that line of best fit crosses the y-intercept, and that point is at $13,199.03. Now, you'll recall from a previous lecture that I told you that if we're interested in predicting y, then we should be using simple regression. But if we're interested in explaining y, then we should be using Pearson's R. And the reason is that simple regression is based on an unstandardized coefficient, that is to say b, and Pearson's R is based on a standardized coefficient that's always between -1 and 1. So let's take an example now of how we might use the equation that we've solved for in order to predict a value of y given a particular value of x. We know that b is 7,875.37. We know that a is 13,199.03. So let's assume that we want to estimate hypothetically, the annual income of an individual with an attractiveness value of 1. So if you look at our data set, there isn't anyone that fits that. There is no one with an attractiveness value of 1 in there. But if you were hypothetically interested in this, you simply have to fill in the blanks. So we have y prime, that's our predicted y, equals bx plus a, where x equals 1. So this is attractiveness level equals 1. And then simply fill in the blanks with the b and the a that we already know. And then you can predict y as 21,056.40. So for an individual who has an attractiveness level of 1, we can estimate using simple regression a yearly income of $21,056.40. Okay, so we've just gone through an example of how to use simple regression to solve for b, our coefficient, and a, our y-intercept. Now let's go through an example using the same data set, but this time looking for Pearson's R rather than b. Right? So Pearson's R is a standardized coefficient that says something about the strength of the relationship between x and y. And because Pearson's R is standardized between -1 and 1, the y-intercept is always 0, so we don't need to include a in the equation, right? The y-intercept simply drops because in a standardized equation, the line of best fit always touches the y-axis at 0. All right, so you might recall from a previous lecture we talked about residuals, and these are the distance between each data point and the line of best fit. So if we're talking about a relationship that is strong, that is to say a relationship that has a Pearson's R value that is positive and close to 1, then those data points tend to be quite close to the line of best fit, that there's a small amount of error or residual error. If the dots are far away from the line of best fit, that demonstrates increased error in our model and therefore a weaker relationship. All right, so let's take a look now at how we can solve for R using the same data set that we used to solve for B and A. Okay, so here you can see the basic calculations, the equation for Pearson's R. It seems a bit intimidating at first glance, but it's actually not that intimidating if you break it down into its constituent parts, as I've done with the data set on the right-hand side of this slide. So again, you can see the respondent in the first column. We can see that there's 20 people. Our X values in the next column, that is the attractiveness ratings. The Y values in the next column over, that's the income. X squared in the next column over, Y squared in the next column over, and then X times Y. And then along the bottom, you can see the various summations. So once you have this basic math done, then it's simply a matter of plugging in those values as such. All right, so starting at the top and working your way down, all you do is you plug in the values that you can derive from the right-hand side of the screen from the data set there. And if you work your way down from the top to the bottom, you will find that R equals 0.77. Right? So what does that mean, an R of 0.77? First of all, we should take heart in the fact that our R value is indeed between -1 and 1. So remember, if you've done the math and your R value is greater than 1 or less than -1, it means you made a mistake, because by definition, Pearson's R is always between a low of -1 and a high of 1. So it appears that we've done something right here. But the big question is, what does that R of 0.77 actually mean? Well, what it means is that there is a positive relationship between X and Y. We already knew this because we've already done simple regression and found that B is a positive number, right? So if B is a positive number, then R must also be a positive number. If B is a negative number, then R must also be a negative number. If B is 0, then R must also be 0. But remember, B has no scale, right? It can go up to infinity and it can go down to infinity. But R does have a scale. It's always between -1 and 1. So this R value of 0.77 is what you would call a strong relationship. So I've given you a little breakdown there on the screen. Obviously, if you get an R value of 0, not only is that a weak relationship, that's no relationship at all. And as you work your way to the right and to the left, you can see that as a number, as in a coefficient, gets closer to 1 or -1, it becomes even stronger. And the general cutoff that we use is 0.7 or -0.7. Obviously, as with simple regression, the proof will be whether or not the p-value associated with these coefficients suggests generalizability. Generally speaking, with a R value of 0.7, the P would also be statistically significant, that is to say less than 0.05, but the proof, again, in terms of generalizability, has less to do with R and much more to do with P. Okay, the last important concept that I want to teach you about in relation to regression analysis is what we refer to as the coefficient of determination. And the coefficient of determination is essentially r squared. So if you've calculated Pearson's r, whatever that number is, when you square that number, that gives you the coefficient of determination. And this is kind of an interesting statistic. Essentially what the coefficient of determination tells you is how much variation in your dependent variable is explained by your independent variable. So how much variation in y is explained by x. In the case of our example, our r equals 0.77. If you square 0.77, you get an r squared of 0.59. So how do you interpret that 0.59? What you do is you turn that into a percentage. So 0.59 multiplied by 100 gives you 59%. And what that means is that perceived attractiveness explains 59% of the total variation in income, right? So we refer to this as systematic variation, variation that is explained by our independent variable. Now, obviously, if we're only explaining 59% of income, that means that we're not explaining 41% of income. And the reason is that income is affected by a large number of variables that we haven't measured. So remember back when we talked about the initial equation, y equals bx plus a plus e, and we drop the e, which is the error term. Well, the e is essentially this 41%. It's a bunch of variables that we haven't actually measured, and therefore we weren't able to incorporate into our equation. And we refer to this as stochastic or random variation. Obviously, if you get an r square of 1, this means that you've explained 100% of your dependent variable. Okay, let's summarize the key points that you learned in Chapter 8. We looked at two methods, simple regression and Pearson's R. These are essentially the same method, but they describe the relationship in different terms. So simple regression describes the relationship in unstandardized terms, in raw terms, and Pearson's R describes the relationship between x and y in standardized terms. So there are two ways of expressing the same relationship between x and y. And the result of both tests, both simple regression and Pearson's R, is a coefficient. So a positive result implies a positive relationship between x and y, and a negative result implies a negative relationship between x and y. And you'll remember that a positive relationship means that as x increases, y also increases, and a negative relationship means that as x increases, y decreases. But remember, we can't say that x causes y. We can say that x is associated with y or related to y, but we want to avoid the language of causation. You'll recall that simple regression, which uses unstandardized B, is best for predicting values of y, whereas Pearson's R, which uses a standardized method, allows us to understand the strength of the relationship between x and y. The coefficient of determination, or r squared, tells us how much variation in our dependent variable is explained by our independent variable. And of course, as with the other statistical tests that we've learned, the p-value associated with either your simple regression equation or your Pearson's R equation will tell you whether or not that relationship is generalizable from your sample to your population. I would ask you at this stage to pause the video and go through either individually or in groups each of these 6 questions, which will help you better understand the material that you've learned in this lecture. Thank you very much for bearing with me, and I look forward to catching you later when we jump into Chapter 9. Bye, everyone.